Okay, great. Welcome to this week's One Word Mind seminar. Our speaker is Weilin Li, an assistant professor in the Department of Math at the City University of New York. Before that, he was a current instructor at New York University and received his PhD in math from the University of Maryland, College Park. His research is focused on applied and computational harmonic analysis. Broadly speaking, he analyzes and develops numerical methods that decompose and reconstruct the data. And today, Weilin will talk about something related to spectral estimation. Weilin, it's your turn.
Okay, thank you very much for the introduction. I'd like to thank all the organizers for their hard work. Um, yeah, so it's my second time speaking at the One World Mind seminar, and I've decided to talk about something that's a continuation of well, maybe not continuation, but it's related to my previous talk. So hopefully there's some kind of continuity here. Yeah, so let me just get right into the problem I'm interested in. I've studied this problem for many years now, and it's the spectral estimation problem. It goes under various names as other equivalent names, such as like super resolution, sparse spike recovery, and so forth. It's an inverse problem. The idea is there are certain parameters, theta and a. The theta you can think of as frequency and a as amplitude. And so these guys, you create some kind of like a Fourier type sum. So this is why theta you can think of as the frequencies and a as the amplitudes. There's S many, you create this Fourier sum, you add some noise, and what you observe are noisy samples at a collection of x's. And for the moment, let's just say that they're equally spaced samples from like minus m. The exact numbers doesn't matter, but from like minus m to m. Um, so I'm following mainly compressed sensing notation. So if you're from that area, then this notation will probably make more sense. So m is like, roughly speaking, the number of measurements. S is like sparsity or the total number of elements. And everything has been kind of like deodorized and cleaned up in a nice way. So the frequencies, I assume they're on the torus. By some rescaling, we can assume all the amplitudes and absolute value are at least one. And then like the sampling set are integers, which makes sense under this assumption on the frequencies. Um, just to be clear, this is like a math talk. I'm not going to say anything about applications or how these things are used, even though I've worked on some of these applications myself. But this is just like a pretty basic problem, and more complicated versions do appear in actual applications. Um, so there's a fundamental concept related to this problem, and it's roughly speaking, it was studied by various physicists. So the idea here is if you think of thetas as being in space instead of frequency, and you just think of them as like certain like point sources, so they emit light. If you observe them under a microscope, you might see a blob. So if the point sources are far apart enough, you might get like two blobs like this, and you would say that, hey, there's like two point sources. And so if you put them close enough together, you might end up on the picture at the right where you see a single blob, and it's not clear if there's one or two or multiple point sources there. So Rayleigh gave this like heuristic criteria, which he says that there's some critical separation where the two sources can be resolved. And this is called the Rayleigh length. This is purely heuristic. And I would say Donohoe in 92 was one of the first people to really analyze this problem mathematically. And in the setup of this problem, where you have 2m, roughly 2m measurements, the Rayleigh length is pi over m. So it's really 2 pi, the length of the torus, divided by 2m. So it's pi over m. This is like kind of the critical scaling of this problem. And everything revolves around the relationship between the Rayleigh length versus the minimum separation, which is how close the frequencies can be. And in this problem, there's really two regimes. There's the first regime, which you can think of as either the frequencies are far apart enough relative to the Rayleigh length, or you can think of as the sample as being large enough such that this condition is fulfilled. So this is like the better case because you have a lot of measurements relative to the separation, and the problem is very stable. So in this talk, I'm going to be looking at this regime only. And really, the question we're after is what is really the best thing you can do in this case? It's not absolutely clear a priori, but it turns out that if you're in this regime, the separation doesn't matter and the sparsity doesn't matter either. So any reasonable algorithm should either not depend on these things or just have a very weak dependence. And the only thing you really care about and want to keep track of is m and eta. So m is like 2m is roughly the number of measurements and eta is the noise. There is the complementary case where you can either think of it as like the samples not being big enough or the frequencies are too close to each other. So in this case, in the language of inverse problems, this problem is mildly to severely unstable. And so around 5 years ago, I gave a talk, talked about the Esprit algorithm in this setting. And the main result roughly says that, okay, if you use Esprit, you can recover these frequencies up to this accuracy. And there's a lot of parameters here, but basically lambda is like the size of like the cluster. So the smaller delta is, the closer the frequencies are, the more frequencies you have in like a tightly formed cluster, the worse the problem is, the more unstable it is. And that's reflected in this like constant here, which can be huge if delta is very small. And so if you think of this huge constant as like the condition number for this problem, the only way you'll get some reasonable result is if the noise is very small. And so, yeah, the more frequencies you have that are tightly bunched, the smaller the noise has to be to get anything good. And what's perhaps surprising about this is that the delta can be arbitrarily small. So in a sense, at least in more mathematical perspective, there's really no like diffraction limit. You can resolve frequencies or point sources to arbitrary precision as long as the noise is sufficiently small. On the other hand, there's this lower bound by Botenkov and others. So there is a gap between the achievable bound by Esprit and the lower bound. So as far as I know, there's still no provably optimal algorithm that achieves this minimax rate as of today. Yeah, so if when Mark uploads this video, I'd appreciate it if you could maybe link to my previous talk. But if you're interested in this case, you can check out this talk and it's still pretty up to date. But here we're really going to look at the good case where basically the advantage of looking at this case is you can let S be very large and it'll be very robust to noise. Okay, so there's really three main goals. And it's kind of, I've organized this talk in kind of like a reverse order than usual. So normally you would describe your like motivation methodology first, but the algorithm will be sufficiently complicated that I think it will be easier to just first describe the results. I'll explain the algorithm later, but in the results section, we'll treat it as a black box. And then in the second part of the talk, I'll explain how the algorithm actually works and why it might be interesting. So hopefully the results will be interesting enough that you want to learn more about the actual method. And then in the final part, I'll talk about some generalizations and why one should care about this. So really, hopefully, even if you're not interested in spectral estimation or kind of Fourier transform stuff, the method we'll use is of like a non-convex optimization method. So, and there's a lot of people interested in such methods these days due to data science and machine learning and so forth. Okay, so I'll describe the results first. Okay, so here's the first result. Okay, so this is joint work with Albert Fannjiang at UC Davis and Wenjing Liao at Georgia Tech. And the result is as follows. So here n controls the number of measurements. It has to be large enough. And you pick any parameters such that we're in this separation regime. So here the frequencies are separated by at least 8 pi over m. let's say all the amplitudes are bounded by 10. This 10 does not matter. It's purely stylistic. It's so that I don't have to keep track of the L infinity norm of A. But the A pi does matter. This is quite important. So this is like the signal class, if you want to think about it this way. The second line is about the noise. So you pick any p that you want between 1 and infinity, and you assume that the LP norm of the noise scales like m to the power of 1 over p. Okay. There's this algorithm that's completely black box in the statement. I'll explain what it does, but it's some iterative algorithm. And it'll produce some iterates that converge at a linear rate to some parameters. The tildes are going to be approximations of the true thetas, such that the error scales like this. It's the LP norm of the noise divided by m to the power 1 plus 1 over p. Before I explain why this might be interesting, I will just say that there are a lot of features of this bound that's sharp. So if you're in this setting where the number of measurements times the separation is at least a pi, this bound that you get is minimax optimal, which means that no matter what other method you use, in general, you can never beat this rate in terms of the noise level and n. On the other hand, if you want this conclusion to hold, you do need a separation condition of this nature. So once this a pi, if you try to replace a pi with a constant that's too small, you're in the opposite regime of this problem, and that's related to the previous One World Mind seminar talk that I gave. And then finally, this noise condition on eta is also necessary in general. Otherwise, you can't recover the thetas and a's regardless of what method you use. Okay, let me try to explain why this might be interesting. Okay, so let's say you look at the case where p is infinity. That's the L infinity theory of this problem. So let's say you just fix your favorite thetas and a's. And by assumption, we have to assume that the L infinity norm of eta is sufficiently small, constant. If you look at the noiseless signal strength, which is the y without the tilde, versus the eta, neither depend on m. It's because y here is a sum of sinusoids, so the L infinity norm is roughly bounded. And the a's are fixed, so you do the L infinity to L1 bound. But the noise strength is also fixed because we're measuring the noise in L infinity. But the conclusion of the theorem is that the error scales like the L infinity norm of the noise divided by m as m goes to infinity. This is basically telling you that you don't need to collect more accurate samples to get a better estimate of the thetas. You can fix the amount of noise that's injected into every sample. And as long as you use more measurements, this error will go to 0. So in other words, yes, it's if you want the error to go to 0, it's sufficient to let eta and L infinity go to 0, but it's not necessary. You can fix the L infinity norm of eta and just let m go to infinity, and that's oversampling. And I'm not cheating here because as we increase m, the assumption relaxes. I'm bounding eta and L infinity, which is independent of m, and so forth. So this is not achieved by assuming that some quantity goes to 0 as m goes to infinity. You could also recast this in L2. So this would be like a noise to signal ratio type of theory. So again, you fix your favorite parameters. We need the L2 norm of eta to scale like square root of m. So if we calculate the noise to signal ratio for this problem, it's the noise energy squared, or noise energy divided by signal energy, which in this case is L2 norm of eta squared over m. And the theorem tells us that the error between the true and recovered frequencies scales like the square root of the noise to signal ratio over m. And so this has a similar interpretation. Yes, if you let the noise to signal ratio go to 0, the error will also go to 0, but that's sufficient but not necessary. You could fix the noise to signal ratio, which means that you don't have to collect more and more accurate measurements. you can fix the amount of noise to signal. But by utilizing more samples, you can push the error to 0. And this is yet another example of oversampling here. Let me just quickly compare to previous results and explain why they're new. So I've chosen 4. There's more other algorithms you could use for this problem, but these 4 are pretty standard types. So the first is like Prony's method. So this is the oldest. It's not possible to really even talk about this problem because Prony's method doesn't use more samples. If you had collected more samples, they would just be discarded in this algorithm anyways. For Esprit, this is another super popular algorithm. If you're in the same separation regime, we were able to get this bound in 2020. And this is not optimal. So the optimal rate would be m to the 3/2 in the denominator here. And this does not have the same interpretation. So in fact, this kind of has an opposite interpretation. If you recast this in L infinity using holders, the square root of m term would disappear. And this would have the opposite effect. It would be like saying, hey, if I increase m, the error is only proportional to eta in L infinity. So there's no point using more m. I'm not improving the estimate at all. It would actually just say, hey, I should pick m big enough until I'm in this regime and then stop. Because if I use larger m, I have to process more samples, the algorithm's more expensive, and so forth. There's no point in doing that, at least according to this bound. As for convex optimization methods, these were popularized by okay, sorry for this typo. So this is Candes and Fernandez Granda here. They wrote 2 influential papers, 2013, 2014. And some other people, they use, these are like analogs of L1 minimization for the continuous domain. This is also not optimal. It has the square root of the noise here. On the other hand, there are some optimal results for sparse Fourier transform with some caveats. So if you are given continuous samples in some interval and you relax the separation more, you can get like an optimal rate. So this is optimal in M, but you do have to pay a price in the separation. So here, if you plug in this delta for here, you'll see that the separation, instead of getting a constant, you'll have some S, M, and noise level dependence here. So roughly speaking, like these results for Esprit and convex methods, they're separation optimal, but the conclusion is not rate optimal. Whereas for the sparse Fourier transform method of Price and Song, you can get rate optimality, but you have to sacrifice the separation of it. And anyways, I mean, people care a lot about the separation and stuff because it has to do with this diffraction limit and so forth. And there are people who are even interested in like the exact constant for these separations as well. Okay. So there's yet another kind of feature of the spectral estimation problem beyond oversampling. So this is for deterministic or adversarial noise. If you try to use this result for like random noise, you will get something that's suboptimal. And that's because there's like some kind of low rank structure. And it turns out it's more like some low rank, like low dimensional manifold structure actually. So here's our theorem for non-stationary independent Gaussian noise. So the signal class assumption is still the same. M is big enough. You have the separation. The amplitudes are bounded by 10, let's say. And let's say the noise is IID. It's not IID Gaussian. It's non-stationary Gaussian, but independent. So the covariance matrix is a diagonal matrix. And it has a certain parameter R here. So depending on if R is positive or negative, it tells you whether the variance increases or decreases over the range of sample points. So probably the easiest case to think of is R equals 0. And then in that case, eta is IID Gaussian noise. So with probability, at least 1 minus little over of m, the exact dependence is in the paper. I just don't want to show it here. Gradient music will converge at a linear rate to these theta tildes, satisfying this rate. So you see that as you increase R, things get worse, which is as expected because you're allowing the noise to grow. But you can also allow for like negative R, which will improve the rates. Okay. In terms of optimality, for R equals 0, this matches the Cramer-Rao bound derived by Stoica and Nehorai in 1989. This is and as for IID Gaussian noise, Esprit is also optimal. This was recently shown by Ding et al. In 2024. As far as I'm aware, these are the only two optimal results for Gaussian noise. We were interested in non-stationary independent Gaussian noise because of this paper by Lexing in 2025 due to some applications to like quantum computing. He wanted to look at non-stationary Gaussian noise, at least using nonlinear least squares with good initialization. And rather interestingly, this rate that we get for gradient music matches the rate that he derived for nonlinear least squares with good initialization. And also both methods fail when R is bigger than or equal to 2. So in the case where R is not necessarily equal to 0, I can't claim that this result is optimal, but I suspect that it is, and somebody just has to show it. At least I'm not aware of any lower bounds for this problem. Let me explain why this might be interesting. So let's consider this example where the noise is growing. So R is 1/4 here. So here's like an example. So like you fix your favorite A's and thetas, and the blue curve is the real part of the signal. These red dots are the samples you collect. As you can see, you get super noisy samples because, well, R is increasing. So as you go out away from 0, the variance of the noise is increasing. So you get these like super noisy samples. But intuitively, you might think like, well, maybe I should stop after a certain point. Because if I let M go off to infinity, the samples I get are so noisy that you might say like, oh, it has no information anymore. I'm just collecting noise. But that's actually not true. According to the theorem, even though the variance of the noise is increasing, the error decays like M to the 5/4. So the theorem actually tells you that, hey, just keep collecting more and more samples if you push M to infinity, even though the variance is like going to infinity, it doesn't matter. You're still collecting more and more information. And this rate is exactly what we see in numerical simulations as well. Yeah, so hopefully, these results are interesting, and I want to say a little bit more about how we get them. So in this next part of the talk, I need to explain at least a little bit how everything works. So we're building off of this original, or we're going to call this the classical music algorithm. And it was created in roughly 1986 by Schmidt. It stands for multiple signal classification. This is one of the most highly celebrated algorithms for spectral estimation. You can see it's been cited over 20,000 times on Google Scholar. I'll just briefly explain the mechanisms. The exact details aren't that important, but I'll let you know what are the most important things. So the first step here is some kind of like denoising step. You let U tilde be the leading S-dimensional left singular space of some kind of Hankel matrix. So basically you lift this to like a matrix. You lift the samples to a matrix, which has some kind of low rank structure, and then you use the truncated SVD or your favorite alternative to this to get some basis for like the leading subspace. So here you're just like denoising it, getting rid of a lot of noise. This part is not super special. What's special about music are steps 2 and 3. So it creates some kind of function, which I'll call this the music function. The notation is Q tilde, it's defined on torus, and it's been normalized. And it looks kind of funny. So Q tilde is defined as the L2 norm squared of the orthogonal projection of phi omega. So we're projecting to the complement, orthogonal complement U tilde. And phi omega has this special form. So for a given omega, which you think of as frequency, you create this vector. And the rows are indexed by the integers from 0 to n-1, and you normalize it by 1 over square root of that. Okay, so you create this function, q tilde, in this way. And then the algorithm says, okay, find the s smallest discrete local minima of this polynomial. It turns out to be polynomial, and we call them the theta j tildes. And you do this through a fine grid search because this function in general, well, it's a polynomial. It's always going to be nonconvex. So why does this work? Why is this a good thing to do? And it's mainly heuristic. If you look at the noiseless function q, so this is the one you would get if there happened to be no noise in the data whatsoever. Q has a special property that the true frequencies are its zero set. But when there's some noise, if you just plot what this function looks like, it appears that the s smallest local minima of the noisy function approximates the true signal frequencies. So you can kind of see it in these figures, and here's a zoomed in one. You see that the blue curve, which represents the noiseless function, has a 0 at 0.2 times pi. But the noisy version does not have a 0, but its local minima looks kind of close. Okay. And the classical music algorithm is very expensive. Even though you're evaluating a function, you normally think of function evaluation as a very cheap type of process. It's not, because you have to do this kind of matrix vector product, which means that every evaluation is on the order of m times s. So if you evaluate q tilde on a fine grid, it's actually quite expensive. Making both of these figures actually requires a bit of time. And this is the main downside of the classical music algorithm, at least computation. Okay, so our idea is incredibly simple, incredibly naive, I would say. If you just look at how this function behaves, it looks like it has a bunch of wells, and the wells are kind of close to the true signal parameters. Well, instead of sampling the function on a super thin grid, you could sample it on a coarse grid, like what's being done in this figure here. And if you threshold, so in this case, we're thresholding by 1/2. If the value of the function at a point is bigger than 1/2, we just ignore it. But if it's less than 1/2, we keep it. And you'll notice that, hey, it looks like these green points, which we keep, are in the basin of attraction to the local minima. So if you keep one of these green points and use it as your initial point for gradient descent, you can run gradient descent and hope that it converges to the minima of q tilde. And if you do this, it's going to be much more efficient. So let me just quickly explain this. So classical music, you have to evaluate the function on a fine grid, which means you suffer from discretization. So the accuracy of the approximation depends on how fine your grid is. And the more accurate you want, the more expensive it is, because you have more grid points that you have to evaluate this function at. So as far as I know, the best way to do this, like the cheapest way, is through the f of t, because q tilde is like a trigonometric polynomial. You can do this with f of t. To get error like epsilon over m, this is the cost, and you can see that it scales like 1 over epsilon, which makes sense because you have 1 over epsilon grid points. On the other hand, gradient music does not suffer from discretization because we're running gradient iterations, which aren't tied to a grid. But the main appeal here is that the coarse grid you can pick to be to have width on the order of 1 over m, which reduces the cost of evaluation. And on the other hand, gradient descent is very cheap. It'll converge at a linear rate. So just to compare, to get error epsilon over m, you see that the dependence on epsilon is much better. You get only a logarithmic dependence because we're doing gradient descent and it converges at a linear rate. And the first term you get here is just evaluating the function on the coarse grid using, say, f of t. So just to give like a simple example with 1,000 measurements, if we use classical music on like my laptop, it would require like roughly 100 seconds, but with gradient music, it's like half a second. Okay. So at this point in the talk, you might not be so pleased because it looks like we're starting with a heuristic algorithm, which is classical music, and doing non-convex optimization, which is also usually a heuristic method. So it seems like it's a doubly heuristic algorithm. So why should this work? Why should you do this? And to really answer this question, we have to answer like a whole set of questions. So the first type of issue we have to address, it has to do with approximation stability. And this pertains to both the classical and gradient versions. So first of all, why does the music function even have S local minima? It's not clear at all. And why would you even want to find them? Like, why would the local minima of the noisy function even approximate the true ones? And in this remark here, I just give like a very basic toy example illustrating how you can have two functions that are very close in L infinity, yet their global minima are super far apart. So, just because, the noise is small, and so if the noise is small, you could say like, oh, Q tilde is close to Q, but that doesn't really say anything about its minima. We don't really care about Q tilde versus Q. We care about theta tilde versus theta. Um, And then the second host of issues are more numerical and computational. So this pertains to gradient music. So why does thresholding work? Why does gradient descent even converge? How do you pick all these parameters and so forth? So the main technical contribution of our work is this horrendous looking theorem, which in words basically says that this picture that I've shown you is the picture that you will always get under reasonable assumptions. So more specifically, uh, if you start off with any m that's big enough, any set of thetas that that satisfies the same separation condition, and you get your hands on any u tilde, let's say using the Hankel matrix, that's accurate enough in the sense that the projection onto the true guy versus the perturbed guy is smaller than 1 over 100, then the music function has these properties. So the first property is of an approximation nature. It controls how close the deepest local minima of Q tilde are to the true signal parameters. And it scales like delta, which is this projection error divided by m. So in other words, they're very close. So, this is already a small quantity, and then you get another extra 1 over m factor here. The rest of the properties are more computational in nature. So 2 tells you that if you're in this O of m neighborhood of any of the tildes, thetas, then the function is actually strictly convex. So that's what you see here in this bottom picture. Now, if you're slightly further away from the theta tildes, then yeah, the function might not be convex, but the derivative has the right sign, which tells you that if you do gradient descent, it'll push you in the right direction. The fourth and fifth properties have to do with thresholding. So the fourth one says that the desirable minima are very deep. So the value of Q tilde at the theta tilde is bounded by delta squared. And this is not a typo. So it's squared in delta. It's extremely small. If you think of delta as like a noise to signal type term, then you get like an extra square here. And the fifth property tells you that the undesirable minima are shallow. So if you're far away enough from all the theta tildes, the function is kind of large, which justifies why this acceptance rejection criteria works. All of these numbers are explicit. So in the paper, we give explicit numbers for parameters of our algorithm, from thresholding to number of iterations, to gradient descent, step size, and so forth. So if there's time and or interest, I can explain a little bit on how this result is proved. It's really the main technical result of our work, and the previous theorems I showed are almost like easy consequences of this theorem. Okay, so why is this approach interesting? I want to compare it with something more standard that you may have seen. So the two standard methods are maybe like nonlinear least squares or maximum likelihood estimation. So there's two S unknown parameters, the thetas and A's. So for both methods, you would create some objective function of two S variables, and then try to find the best ones that minimize some kind of error. So like, some L2 error, or you try to maximize the likelihood functional or so forth. The danger here is that S, the number of frequencies, can be very large. It can be arbitrarily large. So this is doing optimization in a very high dimensional space. And the worry here is that, well, if the objective functional is non-convex, which is what you would expect, then the basin of attraction might be very small, especially in this high dimensional space. And this is in a slightly different setting from how we're doing this problem. These two papers, they calculate the basin of attraction for nonlinear least squares and has radius on the order of delta, which means that if you let S grow, the measure of this ball shrinks. So it's very hard to find good initialization for nonlinear least squares. On the other hand, what we end up showing is quite different. So this, regardless of how large S is, the music function is always a function of a single variable. So we're always doing optimization in like a low dimensional space. But in composition, the landscape is perhaps very oscillatory, has a lot of spurious, undesirable local minima. But the geometric analysis shows that the basin of attraction to the ones that we want have size 1 over m, and that the music function is large away from these basins of attraction, which means that initialization can always be found efficiently by evaluating the function on some kind of grid or non-uniform grid of mesh norm on the order of 1 over m, which means that initialization for gradient descent can be found easily and efficiently. So basically, to summarize, this method is very different from what you would normally see in like non-convex optimization. It's really something, it's really about designing some landscape that has some nice properties where you can actually do optimization in a rigorous way. Okay, so I hope it's clear that what we're doing is fully rigorous. And we're not doing this in a heuristic way like you would see some other optimization approaches, let's say. In the next part of the talk, I want to say a little bit about why this approach is interesting, why it's general, and what other problems you can use this for. So one of the problems we can look at is this multidimensional version. So here the frequencies are in d dimensions, let's say, and you have a multidimensional like Fourier sum that's been corrupted by noise, and x star is the sampling set. Okay, so here x star is arbitrary. I want to keep it this way for now because there's a lot of interesting sampling sets in several dimensions. Unlike 1D, in one dimension, there's really only like one type of uniform sampling set you can consider, but in higher dimensions, there are a lot. Right, and so how do you solve this problem? So, for experts on spectral estimation, people know that the higher dimensional case is quite a bit harder. And it's not only just of a computational nature, it's because if you try doing kind of the most natural or naive thing using projections, something bad happens. So let's say x star is some kind of continuous set, such as a ball. Just think of a disk in 2 dimensions. If you take the samples along some kind of line, you can interpret this multidimensional sum, exponential sum, as a 1D version with some effective nodes, which is theta j dotted with u. and u is the direction of this line. So the idea here is like, okay, I can reduce like a two-dimensional problem to a collection of one-dimensional problems, and then use my favorite 1D algorithms that I have. Now, the problem here is that, well, if you project onto directions, you might get some bad ones. So for example, if I try to project to these three guys onto the canonical directions, these two will collide, which will be quite bad because now this 1D problem is no longer solvable. Okay, you could argue that this doesn't really happen if you do like random directions. So maybe the second picture is a bit more accurate. But if you do the same thing, you could turn this very stable 2D problem into a collection of two 1D problems, where one of the 1D problems is extremely unstable, because now this projected distance between theta 1 and theta 2 is very small. And once you're in the regime where the separation is too small, it becomes very sensitive to noise. And of course, it's hard to figure out what are the right directions because the thetas are unknown. This is what you want to know. That's not to say you can't get this to work out. So I think since I'm running a bit low on time, I won't say too much, but you could do like random projections and then have some kind of rejection criteria, as was done in Chen and Moitra. There are some like multidimensional Esprit algorithms that in essence are doing projections, and then there's ways of trying to mitigate bad directions and so forth. But I would say the multidimensional case is quite open. There's still a lot of unknown results for many of these algorithms. But for music, gradient music, the extension is simple and straightforward. So in the 2D case, what I would do is compute this music function, which is a function of now two variables, let's say. So this is like a contour plot of what it would look like. I would evaluate it on a coarse grid to find good initialization, and then use gradient descent to find the local minima. And here in this picture, the red dots represent the true signal frequencies. And you see that the basins, the basins of attraction here are on the order of 1/m. So they're quite wide relative to the accuracy that we can measure, that we can estimate the signal frequencies at. The landscape is a bit more oscillatory than what's seen here. So there's like a lot of small fluctuations that don't appear in the contour plot. And this figure here is like a zoomed in figure of this guy. And you can see that the basin of attraction look like some nice balls here. Okay. All right, so let me just state our main result when you sample in a cube. And this cube has side length 4m. So again, you look at any thetas, any a's, and you're in the separation regime for a big enough constant that only depends on the dimension. If the noise here in LP has the scaling, then gradient music will produce iterates that converge to some theta tildes, and the theta tildes are close to the true signal parameters. It scales like this. And if you formally plug in d equals 1 into this expression here, it matches what we got in the 1D case. We also have a version for random samples. So let's say you take a G, which is ID Gaussian with variance sigma squared. And let's say you tack on a term that can grow or decrease in the magnitude of x. In this case, this is the error bound that we get. Okay, so let me know if I'm running out of time and I need to speed up. Okay. Let me just say a little bit about why this is much better than classical music. Basically, it's the curse of dimension. In d dimensions, if you want a grid with mesh norm epsilon over m, then you need m divided by epsilon to the power of d grid points. And this is what you would have to do with classical music. And this is the complexity you get, which behaves very poorly on epsilon. With gradient music, you just need a coarse grid of width 1/m. which means the number of grid points you get is independent of the accuracy epsilon that you're trying to achieve. Instead, the dependence on epsilon is very mild. You just get a logarithmic term. That's again because we're doing gradient iterations, even though in higher dimensions, these gradient iterations are very cheap. Okay, so at the risk of maybe saying way too much, what we're doing with gradient music and this theorem here is actually a special case of a much more general framework. It turns out that if you want to deal with arbitrary sampling sets, which can be continuous or discrete, arbitrary domain, arbitrary noise, there is a general way of doing this. And it follows roughly the same steps with some generalizations. So there's some way of processing your samples, some way of finding a projection operator, some way of defining some kind of generalized music function. And then you do, this initialization and optimization procedure. And what ties all of this together is that there's a certain kind of measurement kernel, which depends on the nature and the structure of your sampling set. So this guy is basically just the inner product of these phi's, which has this form. And there's a certain meta theorem in our paper. So if this kernel satisfies some good properties, then the gradient music algorithm provably works. And this is the error rate you get. So it depends on your initial error for this projection. But the entire point here is you get this extra factor here, which depends on this h. So h is the negative Hessian of the kernel at 0. And it's the square root of the trace over the smallest eigenvalue. So for favorable situations, this can be a very small quantity. Like in the 1D case, this is how this 1 over m appears. And yeah, so for examples of kernels, in the 1D case, it becomes this normalized Dirichlet kernel. If you look at samples on a cube, you get the square Dirichlet kernel, which is some tensor products of these 1D guys. If you look at continuous samples on a ball, you get some kind of weighted Bessel kernel. And you can look at other shapes as well. So in our paper, we give a full analysis of the second and third. Okay, but you could really play this game with anything else. Okay, so with that, let me conclude this talk. So just to summarize, so yeah, so gradient music, it's optimal in this well-separated case. And it's optimal for various natural, deterministic, and random noise models. And it's fully rigorous. It's a rigorous nonconvex optimization algorithm. And it really hinges on some special properties of this music function when used as like an optimization landscape. It has a very canonical extension to higher dimensions and uses the same mechanisms as the 1D case. And it's all unified by this kernel structure. It's efficient because we can find initialization using a coarse grid that's not tied to the accuracy of the method. And gradient iterations are very cheap, even in higher dimensions. And finally, well, gradient and classical music really output the same things, but gradient music is just more efficient. So there's really no reason to ever use the classical version over the gradient one. And then in the final final bullet point, which I didn't really say much about, is that the method is very flexible. So there's nothing super special about what we're doing here. It's compatible with general sampling sets. You can incorporate some randomized numerical linear algebra tools to increase its efficiency. You can do like random sampling, like compressed sensing theory to reduce sample complexity. And you don't have to even use gradient descent. It's like the most canonical, most basic one. So that's the one we looked at. But you can look at more sophisticated optimization tools as well. If you're interested, I would say it's this 1D case is the most accessible one. The multidimensional case, we're wrapping up the details, doing some polishing, but it should be available on the archive within the next few weeks. And there's a final kind of application of this, which I didn't talk about, and it's to the recovery of low-rank Toeplitz matrices. So yeah, so if you can solve the spectral estimation problem optimally, then you can solve some other problems optimally as well. And that's what we do in this third paper here. So with that, thank you very much for your attention.